My name is John Maddy, and I'm the director of the University of South Wales Hydrogen Research Centre. I'm here today to talk to you about our activity under the H2SHIFT project, and specifically that's about anion exchange membrane testing and the test lines that we're developing. Firstly, just a little bit about our research centre. The Hydrogen Research Centre at the University of South Wales includes a multidisciplinary team combining science and engineering disciplines. And we have significant academic and also industrial experience. In my case, I've got 20 years experience in the industrial gases industry before starting to run the centre. Our sole purpose really is to conduct industrial-facing hydrogen research and development, and that means working with industry partners to develop prototypes towards commercial reality and towards commercial deployment. We've got a significant track record of working with industry in that type of prototype development for hydrogen technologies at various stages. And our key research areas really include electrolytic hydrogen production. We work on the hydrogen recovery of hydrogen and hydrogen purification. We work on hydrogen storage materials, but also the role of hydrogen within energy storage. We work on hydrogen for transport, and that includes component testing, but also vehicle filling. And then we work on hydrogen for industry and looking at the way in which hydrogen can decarbonise in an industrial setting. So we have a significant track record of working on several rounds of different electrolyser prototypes and product testing and development activities. Initially, we started to work on alkaline electrolysis with industrial partners, and we've since operated an extended research program and continued to do so on alkaline electrolysis. But we've worked over the last decade and slightly more with PEM electrolyser manufacturers. We've had several rounds of separate types of PEM prototype testing and product development, and specifically with ITM Power to develop their basic PEM electrolysis to what's now a major industrial product. So looking at our objectives via the H2SHIFT program, our aim is to facilitate significant advances in AEM, anion exchange membrane hydrogen production. And to do that, we're developing AEM electrolysis testing lines, and specifically that includes 1 to 10 kilowatt prototype and research focus lines, as well as a 100 kilowatt technology upscaling line. We're running an AEM showcase, and that's with an SME called Proteum, to establish and to test a 100 kilowatt anion exchange membrane electrolyser at our hydrogen centre. And then thirdly, to coordinate through the single entry point, and I'll explain that, to co-develop further scalable AEM test activities with startups and SMEs. And the graphic on the right-hand side shows the process through which the H2SHIFT program will operate. So prospective technology developers, SMEs, will make contact through a single entry point, and then testing services will be initiated, in our case with AEM technology, and we'll be looking at upscaling that technology, improving the technology, proving the technology activity, and then a range of non-technical services will also be offered in terms of business development and the like, and hence out of the far end of that, an innovative solution, and the technology will be moved closer to commercialization. Looking at anion exchange membranes, the promise really of AEM technology is that it lowers capital cost by combining really the benefits of alkaline and PEM electrolysis. Effectively, it uses cheaper non-noble catalysts and operates in an alkaline environment, so it's more cost effective. It uses less expensive materials, and it avoids extensive use of platinum group metals like platinum, iridium, or ruthenium. And also then enables process optimization, so it combines the efficiency and reliability benefits of both alkaline and PEM electrolysis. So specifically what we're looking to do is to develop electrolysis test lines at 3 levels. Firstly, a 1 kilowatt test line for early prototype AEM technology. So lab scale AEM electrolyzer stacks. And that line will include basic water purification feed activity, small scale power electronics, and then basic gas handling, so low hydrogen output. And that will look at material validation and control logic and testing of that early prototype electrolyzer. We're then developing a 10 kilowatt test line for prototype AEM systems. So this is looking at modular AEM stacks, and then really looking at intermediate water management and balance of plant operation. Enhancing power supply and control, and we've got some specific activity at the moment looking at advanced power management for electrolysis. This type of system would then have gas drying, flow metering, and venting, and then we'd look at running efficiency studies and durability testing for that type of scale of prototype system. And then finally, our largest test line will be 100 kilowatts, and that's about pre-commercial AEM systems, scaling AEM stack systems towards commercialization, full balance of plant integration with thermal, pressure and safety activity, and then advanced monitoring, data acquisition of the system, and then combining that with, in our case, because we're integrating on an existing hydrogen site, hydrogen compression and storage options as well. So in this case, it's field trials, readying AEM technology for real-world performance and operation. If you look at the challenges that we're trying to address, then that's really about membrane stability, starting to develop membrane materials and AEM materials that will be stable and exhibit stability under harsh operating conditions. We're looking at catalyst durability and enhancing the durability and activity of non-noble catalysts in AEM electrolysis. We're looking at improving ion transport and the ion conductivity through the membranes to enhance efficiency and optimize electrolysis performance. And then water management, addressing any water management challenges within the AEM electrolysis system, minimizing flooding and maintaining efficient gas transport at the electrode surfaces. And then, as I hope I've made clear, the whole point is about scale up and cost reduction to take AEM technology towards commercialization. So specifically looking at the Protium 100 kilowatt stack and AEM electrolyzer, that's installed and is operational at the Hydrogen Centre. And we're now going through and have been going through a testing procedure for this well-established 100 kilowatt AEM system. So that's operational performance testing, durability testing, gas purity testing, and then looking at energy efficiency and consumption, energy consumption testing of the unit. We'll also be looking at the economics of the system, how we together with Protium can scale this type of technology. And a significant element of this and any new AEM technology will be doing safety and compliance testing. And a lot of that is about safe design in the first place. So we'll work with SMEs, and in this case we work with Protium, to design a safe system for integration into our existing hydrogen centre, and that's exactly what we'll do with other SMEs through the H2SHIFT programme. So that really is an overview of our activity on the H2SHIFT programme. I'm sorry I'm not there to answer any questions, but you can see here my email address, and I'd welcome any contact from anyone that would like to know more about the AEM testing that we're doing through the H2SHIFT project, but also any other activity that we're doing on hydrogen. So I thank you for your time and hope you enjoy the rest of the day. Thank you.